Okay, so welcome back to the second half of today's session of the course. What we're going to do in the second half is, well, do some more recursive definitions because practice makes perfect. And by the way, I have not said so far for those of you who are watching the lecture from somewhere else. Whenever we start doing an exercise here in the lecture room, you should do the same at home when you watch these lectures, whether live or later on. Served cold like vengeance. So what you should do is, whenever we start doing an exercise, you pause the recording and you do it yourself. And then you can check whether what you're doing is somehow consistent with what we do in the lecture room. The lecture room is the coolest place to do this, but I understand that some of you cannot be here for reasons that I cannot understand really, but that's another matter. Okay, so let's do some more exercise because 10 minutes break is a decent break, but it's a long time, for some at least. We might have forgotten everything that we were doing before and why we were doing it and how we were doing it. So what better way to warm up our neurons again than to do another recursive definition of a function over lists? Can you think of a better way? I can't today. Well, I could in general, but not today. Okay, so here's the specification for you. I want you to define for me a function concat that takes two lists now. Ladies and gentlemen, lo and behold, not one list, two lists, L and L prime, and returns a list which is the concatenation of the two lists that the function gets as input. So it's a list that starts like L, and then when L finishes, it continues like L prime until L prime finishes. So far, so good. And I want you to define this function in that recursively for me. Now, what is the novelty? The novelty, well, relatively speaking, is that now you've got two inputs. So you've got to decide what input to do some recursion on. You could either do recursion on the first argument or on the second argument. Now, what does your intuition say? Is it better to do recursion on the first argument or on the second one? On the first one, your friends here are saying. Why is that? Well, that's because the concatenation of L and L prime starts with L, and then when L terminates, it continues with L prime. So it's a good idea somehow, it's a reasonable idea to try and do the recursion on the first argument, which means that we are going to define the function concat by examining the case when the first argument is empty, and then the case when the first argument is not empty. And if we can do that, then we covered all the cases. So let's do it. Concat of empty list L prime. Well, what should the result be in this case? It should just be L prime, because if you concatenate a list with no elements with L prime, what you get is a list that contains everything which is in L prime. Easy. In particular, if L prime happens also to be empty, you get the empty list back, which is okay, because if you have a list with nothing followed by a list with nothing, what is it that you get? A list with nothing. Writing nothing several times doesn't produce a book, does it? It produces nothing. Well, it could be the book of nothing, but that's it's a very short book. It's a book that most young people love to read. It doesn't take any time today. Okay? So that then we can go back on YouTube and watch a few videos. Okay, what is the other possibility? The first argument is not empty. But if it's not empty, it has the form some bit followed by a list. And the second argument is L prime. So what is the result of concatenating B followed by L with the list L prime? How does the list start? the concatenation of the two starts with B. Okay, and what is it that follows? And now you want to unleash the power of recursion with concat of L and L prime. Bingo! You've defined a concatenation function over lists in 2 lines of code. Just by using recursive thinking. You could, of course, do all kinds of for loops, while loops, and get them wrong. But why should you? You can do this recursively, and you get it right straight away, and you let recursion do the job for you. You just define 2 cases. Is the first argument empty? If it is, return the second. If the first argument is not empty, write a list that starts with the first bit in the first argument and then continues with the concatenation of whatever remained of the first argument with the second one. Surely this works. And not only works, it's beautiful. You know, people in Naples say even every cockroach is beautiful for its mom. Well, since we did this, we are the mothers of this fantastic piece of code, so we love it. Yeah, but it's not a cockroach. It's actually a beautiful a lady or a guy, whatever you prefer. Are we convinced that this computes concatenation? If not, think about it for a while and you will see, yes, it does. Splendid. Yes, there is a question there. Fine. If the first argument, so the question is, can you repeat what you said before? And I said, yes, I can, I hope. Okay, so the first case of the definition, let me call it case A, takes care of the fact that the first argument is empty. If the first argument is the empty list, then concatenating the empty list with something else gives you that something else. Because you write a list that contains no elements, followed by every element in L prime. The only thing you write down is every element in L prime. That's the first case. The second case is case B, that this deals with the case in which the first argument is not empty. Now, if a list is non-empty, it starts with a bit, assuming it's a bit list, otherwise it starts with the element of the data type over which you take elements from the list, and then follows with a shorter list, the rest of the first argument. Okay, so what should the concatenation of this list with L prime be? Well, the first thing is that you write the first element of the first argument. It's the bit B. Now, what follows is everything that remains of the first argument, namely L, followed by every element of L prime. How do you compute the elements of that list? Well, by applying concat recursively to L, what remains, the tail of the first argument, with L prime, the second argument. Yes, another question.
What is concat?
Concat stands for concatenation. It's just the name of the function. It's just the name of, oh, the question was, what is concat? Sorry, I should always repeat the question. So it's just the name of a function. You can call it Snoopy, if you prefer. It's only that since it's supposed to do concatenation, Snoopy is not a very good name. Or Pinocchio, or Goosey, whatever. If it was to compute the length of a nose, then Goosey would be a good name. In Iceland, not nowhere else in the world. Okay? Yes, there is a question. What is concatenation? That's a very fundamental question. Concatenation is...
It's taking two strings and then adding the next string to the end.
Yeah, concatenation is exactly what he said in the world of strings. You just take the elements of the first list, one after the other, and then you append to that the elements of the second list. That's what concatenation is about. Now, you will forgive me, but I don't know the Icelandic word for concatenation. It's first the first argument, then the second one. Yeah, it's only like a splicing. So your colleague is saying splice. It makes me think of genetics. But anyway, sort of whatever, it just means you first write L and then you write L prime, one after the other. If it's terms of strings, you just write them one, the first string, and then the second one. Yes. Oh, the question is my usage of the prime thing. That's just the name of a variable. I could have written X and Y instead of L and L prime. It's just that L is probably a better name for a list because it starts with L. But I agree, sort of X is a beautiful name for a variable. It's a variable of type list. If only we could name all our variables X in our programs, we would be fantastically happy. Okay, so let's do more exercises. One more exercise, come on. I want you to define now a function that takes as input a list, and this function is called rev for reverse, that takes as input a list L and returns a list which is just the reverse of L. So we read it from right to left, Arab style. Okay? So for instance, example. If we want to define the function rev in such a way that if the input is the list 0 followed by 1 followed by the empty list, so the list 0, 1, the result should be 1 followed by 0 followed by. It's just the reverse. You just write it the other way. And I want you to define this function. Guess how? That's not a trick question. Recursively. I want recursion to do the job for us. And in fact, I want you to do the job for me. I just write down what you tell me to write. So what do we do first? We define the function reverse over the base case, the empty list. So what is the reverse of the empty list? The empty list. So far, so good. We can do the base case. Now, what is the reverse of a list that is non-empty? So it starts with B, and then it's followed by L. Okay? So some people in the audience are saying, okay, I want to write the list in the other way, so I want to reverse L, and then I want to stick B at the end of what I get. Because B was the first element of the input, so it should be the last one of the output. And it should be preceded by the reverse of the tail of the list that I get as input, namely L. Now, remember, in the constructions of our data type over list, the only thing that we can do is to take a bit and put it in front of a list that we've already built. We cannot take a list and put it in front of a bit, which is what we want to do. However, perhaps we have defined just before an auxiliary function that we can use in our definition of reverse. This auxiliary function allows us to concatenate two lists. One of them could be the reverse of L. The other one could be a very short list that only contains B. So end of hint. Now you tell me what I should write. Okay, so your colleague is saying, first you reverse L, and you concatenate the reverse of L with B. However, this is conceptually correct, but it doesn't quite type right. Why? Because B is a bit, whereas the second argument of concat is a list of bits. So instead of B, I want to write a list that only contains B. So B of the empty list. You know, types, yeah, I'm implicitly strongly typed myself. I'm not JavaScript. But anyway, conceptually, we were there. Okay, you want to reverse a list of the form B followed by L. What is it that you do? You want to put B at the end. And before the B, you want the reverse of L. That's exactly what this does. Okay, the question is, can't I just write rev L double column B? The answer is no. Why not? Because remember, double column is an operation that takes a bit as a first argument and the list as a second argument. That's how we defined it. So doing it this way would not quite, I mean, morally it would be right, but no strongly typed programming language would actually appreciate the fact that this is morally right. We would complain, because this should be a bit. That's why we need to use concat to make everything typed right. And at your leisure, for instance, you can just now apply this definition, the definition of concat, to this example, and you see that what's the reverse function spits out is what it should. I'm not doing it now. I'm going to let you work at home or later on here. Okay, beautiful. So let's do something else now, which is to say more recursive definitions. But we are going to define something apart from lists. Now, lists are beautiful. They are a fundamental data structure in many programming languages. I'm sure you've used lists. If you haven't, you're going to use them to death in data structures. So you already have, perhaps. Another fundamental data structure in computer science is the tree, and in particular, the binary tree. What I want to show you now is a recursive definition of the data type binary tree. So what is a binary tree? We want to define it recursively. In particular, this is a binary tree where the nodes of the tree store elements from some data type A, capital A. How do we define it? Well, we start by defining the smallest binary tree of them all, and then we give a construction that allows us to build more complicated binary trees from simpler binary trees that we've already built. So what does the first clause say? The first clause says that this lambda thing that I'm using there is a binary tree. Now, this lambda stands for null. It's an empty tree. So the first clause says the empty tree is a good, honest-to-God binary tree. Now, in the textbook, you will see this called the extended binary tree because binary trees, they say they are not empty. But I don't want to discriminate. Why should we discriminate against the empty binary trees? So the binary tree is a good, honest, the empty binary tree is a good, honest-to-God binary tree. No discriminations in this class. Even the empty guy is good for us. Okay, so how do we construct a more complicated binary tree given two binary trees, T1 and T2, that somebody has given us? Well, one way of constructing a more complicated binary tree that uses T1 and T2 is to add a root node, a new root node, which we use to store some element, small a, of our data type, capital A. And then this new tree will have a left subtree, which is T1, the tree, one of the trees that we were given as already built before, and the right subtree, which is T2. This is what this linear notation really indicates. It's a linear notation for trees. Let me draw some pictures just to make these things tree-like. So the first clause said, this guy is an extended binary tree. When I'm going to draw these things pictorially, I'm going to draw these basically null pointers with these boxes. That's a representation of what is really a null pointer. It's the empty tree. It's a pictorial representation of an empty tree. I could, of course, draw nothing, but it's nicer to draw these boxes. Okay, what does this thing stand for? This thing stands for a tree which is non-empty. It has a root that holds the value A, whatever this value might be. It has T1 as a left subtree, and it has T2 as a right subtree. Pictorially, this corresponds to something like this. You have a root node, which holds the value A, and then you will have a subtree on the left that corresponds to T1, and a subtree on the right that corresponds to T2. So this linear notation really stands for, is a representation of this tree that you have over there. Okay, so if you are more pictorial than I am, I'm a very sequential guy myself. I mean, my pictorial understanding is close to zero. I'm not the son of Michelangelo, unfortunately. Okay, so this is how you can think of trees. In fact, I also think of them that way, but this doesn't lead to good scientific theater. Okay? So basically what we've just said is that a binary tree is any tree that you can define by using these two construction rules. Okay? And make no mistake, you will be working with trees quite a bit in the data structures course. So I'm just giving you a head start here. In particular, binary trees are fundamental data structures that you will also work with in algorithms, Reiknirid, in the following semester. Okay, shall we do something with these binary trees? I guess so. Otherwise, what's the point in defining them? So, first question. Well, actually, before talking about the principle of structural induction, let me make you work. Use this definition to define recursive functions that do some simple stuff over binary trees. Now, whenever you have a binary tree, there are two quantities that are typically associated amongst many with this binary tree. One of them is the so-called number of external nodes in the tree. That's what this E stands for here. That's the number of external nodes in the tree. And what are the external nodes? They are the number of occurrences of this lambda, that is to say of the null pointer, in the tree. The other quantity that you may want to associate with the tree is the number of internal nodes. These are the data items that are stored in the nodes in the tree. These were the circles that I drew before. So E counts the number of boxes in the tree, the number of null pointers, the number of empty subtrees that you have in the tree specification. I counts the number of actual round nodes, that is to say, the number of values that you actually store in the tree. Shall we define these functions recursively? Why not? Of course, mine is a rhetorical question. I want you to define them recursively. So let's do it. And of course, if you're at home, you should do the same. You just pause the recording now and write down the definitions. So number of external nodes first. The number of boxes, the number of lambdas in the tree specification. How many empty subtrees do you have? Well, this is a recursive function. How do we define it? First, we define it for the base case. Okay, just a second. This is counting the number of empty subtrees. If the tree is empty, how many occurrences of lambda does it have? If I give you lambda, how many lambdas are in there? So pictorially, this would correspond to counting the number of boxes in the tree, which is a box. So how many boxes is there in one box? One. Okay, that's the base case. How about the inductive case? The inductive case takes as input a tree that looks like this. It has a root node that stores some A. It has a left subtree T1. It has a right subtree T2. Now, how many empty subtrees, how many occurrences of lambda does this tree specification have? So pictorially, this would correspond to this. For those of you who like pictures. Okay, so where are the empty subtrees? Well, the root node is not a null pointer. The root node holds a value. So that's an internal node. This function is supposed to count the number of boxes of empty subtrees. So where are the empty subtrees? In T1 and T2. And how do we find out how many of them are in T1? We call recursively E on T1. How do we find out how many there are in T2? We call recursively E on T2. And how do we find out how many there are overall? We sum the two. That's the number of external nodes. That's the number of boxes in this tree that you have over here. Okay, it doesn't take spider senses from me to figure out that some people are confused. How many people are confused? Let me make a poll. Excellent. In fact, my spider senses were actually quite right. So where is it? What is it that confuses you?
Are the boxes only on like that?
The question is, are the boxes only on the endpoints? Yes, because the boxes are empty subtrees. So they can only occur at leaves. They stick from leaves of the tree, right at the end. You cannot have a box in the middle. The other nodes are all in the middle. They are internal nodes. Absolutely. So just to clarify matters a little bit, let's do the recursive definition of the other function that counts the number of round nodes, the nodes that actually store elements from our data type A. Okay, how many round nodes does the empty tree have? Let me remind you that the picture is like this. This corresponds to a null point. How many round nodes are there in there? 0. There are none. Okay? How many round nodes are there in a tree that has a root that stores the value A, and then has two subtrees, T1 and T2? Pictorially, this is a tree that looks like this. Just to repeat myself. That's T1, and that's T2. Okay, so how many round nodes are there in there? There's certainly one at the root. But is it the only round node in the universe? Perhaps not. How do we find out how many round nodes are there in the two subtrees? We just call the function I recursively. So you want to know how many there are, how many round nodes, how many nodes stored in values are there in a tree that looks like this? Well, you first of all figure out there is at least one, and it's the one at the root. And this corresponds to this one here. And then you say, okay, the other ones, if they exist, they are either in the tree T1. And how do I find out how many there are? I just call I recursively on T1. This corresponds to this recursive call. Well, the other ones, if they exist, are in the subtree T2. How do I find out how many they are? Easy. I just unleash the power of recursion and recursively call I on T2. Now, how many are there overall? I just sum the number of nodes which are round and are in T1, the number of nodes that are round that are in T2, and I add one because the root is round. Okay, the question is, why don't I count the root in the external nodes? Because the external nodes are the square ones, and the root is not square. Note, I count it here when the tree is empty because it contains one square node. Sorry? Question, can you have many roots in one tree? Well, what we are defining are rooted trees, and they have only one. A tree only has one root, otherwise you have a forest. Okay, no, the nodes that I write with circles, they are the nodes that hold elements of the data type. The reason why you will use trees in the data structures course is to store elements from some data type. For instance, integers, keys, to address some element, whatever. So these internal nodes, the round nodes, will hold elements that you want to store. For instance, telephone numbers in a telephone directory, whatever. And then if you organize your tree nicely, you will be able to search for telephone numbers efficiently. The square nodes, as your colleague is saying, do not contain any information. They are representations of null pointers, of empty subtrees. There is a question up there at the top.
I was thinking that it would be a good idea to draw a tree with maybe like 10 nodes so people understand.
Absolutely. The question is, you want me to draw a tree with 10 nodes. You will forgive me if I draw a smaller one. Because I want to draw the linear representation, and then I come to your question on the second one, so just so that I don't forget to draw. Okay, so what tree is this? A1, lambda, A2, lambda, A3, lambda, lambda. Now you will appreciate why I don't draw a tree with 10 elements, at least not in linear notation. Okay, so what is the graphical representation of this thing? Okay, so this is a tree that has A1 as the root. What is the left subtree? The left subtree is empty, so I represent it by an external node, a box. What is the right subtree? Well, it's a graphical representation of this tree. Now, what is it? It's a tree that has a root, A2. Now, what is the left subtree? It's again empty, So I represent it as a box. And what is? So this is the right subtree. You have A3, and then you have two empty subtrees here. So this is a bit of a boring tree, actually, because it's really a list in disguise. But this is how it gets represented. And now if you see, you might want to calculate. So if we call this tree T here, ET, go home. Sorry, this is a movie, it's a different thing. ET will actually count the number of external nodes of the boxes. There are 4 of them. Whereas IT, for information technology instead, would count the number of round nodes, the nodes that actually store elements of the data type that we are interested in storing. There are 3 of them. Absolutely. The only thing that the external nodes do is to count the number of empty subtrees. Absolutely. You may note here that the number of external nodes is 1 larger than the number of internal nodes. That's not a coincidence. This is always true. Okay, so the question is, these are just called leaves? Not quite. So these are not, so the leaves in this tree, in this case, there is only 1 leaf, and it's this one. The leaf is always an internal node. A leaf is an internal node. In this case, there is only 1. And it's the node that has no subtrees whatsoever. Okay, so the question is, what is the difference between the triangles and the circles? The triangles here are trees. The circles are nodes in the tree. Yes, the triangle was just a shorthand for a whole tree. You see, a picture can speak louder than words, but it can also be very confusing. That's why I like this linear notation, which is what the computer uses anyway. So I'm a sort of a computer myself, a slow one, and one that forgets. Okay, so what is it that we've done? We've defined another data type recursively. And this data type is the data type of trees. We have defined 2 functions recursively over trees, which are recursively defined. The external and internal node counters. So one thing that we could do is to actually go ahead and prove this statement that I just made, that the number of external nodes is always 1 larger than the number of internal nodes. I encourage you to try and do this at your leisure, for instance, during the exercise session next week or at home, by using the principle of structural induction, but now for trees. Now, what is this principle? This principle basically says that if you want to prove something for trees, you prove that it's true for the empty tree, and then under the assumption that it's true for the tree T1 and the tree T2, it is also true for the tree that has A at the root, and T1 as left subtree, and T2 as right subtree. I promise you that at the start of the next course session, we will do a similar exercise. And then you assume that the statement holds for the subtrees, T1 and T2, and you prove that it's true under this assumption for the tree A with T1 as a left subtree and T2 as a right subtree. That's the principle of structural induction for trees. Okay, I think we've used our time for today, but there is still always time for questions. Any question? The question is, when is the next class? On Tuesday. The classes are always on Tuesdays and on Thursdays at lunchtime. Okay, thank you very much.